Hey guys, today we're going to look at some exercises related to proving the convergence of a sequence, or proving that the limit of a sequence is something. These are the exercises we're going to look at today. Let's get into it. Now, to be able to show the convergence of a sequence, we have to understand what the definition of a convergent sequence is, and that is something that a lot of young students want to overlook, is the importance of definitions. Math is very good at starting us out in intuitive situations, but if we only rely on intuition, we can only go so far. Understanding rigorous definitions is what helps us get to the next level of mathematics, which is hopefully at this point in your career what you're trying to do. So here we say that a sequence converges, a sequence AN converges to some real number A, and we can write this as the limit of A sub n, the sequence of A sub n equals A, if for any epsilon greater than 0, there exists a natural number n, or it could be a real number n, such that the absolute value of A sub n minus A is less than epsilon for all n, little n greater than capital N. And when I first read this definition, I had no idea what it was talking about. No one really gave me a picture related to this, but I think the picture does make it clear what this is trying to say. So I'm going to try to draw something like that for you real quick. So we're going to draw an axis here, and this is kind of our x-axis. But all I'm doing is marking where my terms in my sequence are going to fall. So for example, A1 may be up here somewhere, and then A2 may be down here somewhere. What we're saying here is if I think my limit point is, we'll call that A, is horizontal line, what I can do is pick an epsilon, and epsilon always represents some number greater than 0 but is very small. So it's very close to 0 but it's a small number. So my friend is going to pick an epsilon value, and what I'm going to show is that after a while this inequality is true. And what that means is the A sub n terms, how far away are they from A? Well, just less than epsilon in either direction. So here I'm adding epsilon and subtracting epsilon, and so I get this kind of bandwidth. We call this a neighborhood. But what I'm saying is after a while, every one of my terms in my sequence will be within that bandwidth, will be inside that neighborhood. And so that n value may be, it may be way down the line, but eventually we get to capital N. And so capital N is this indicator that once I get past capital N, so for all n past capital N, all my sequence terms are going to be inside this bandwidth. Okay? Now that's true for this one epsilon, but it says that to show the convergence, this is actually true for any epsilon. So we did it for this epsilon. We found the n that we needed. Now let's make epsilon get a little bit smaller. We might have to go deeper into our sequence, but we can still find that new capital N, such that after that, all my terms are within that new bandwidth. Okay, so I hope this makes sense. This is how we prove convergence. Now, if you've taken like a Cal course where you talk about the convergence of sequences or limits of functions, we've done it in a very intuitive way, where we can kind of imagine, well, look, if n goes infinity, 1 over n gets smaller and smaller, and so 1 over n trends towards 0. We did it in an intuitive way, but now this is more rigorous, and so this is going to allow us to prove limits that aren't always intuitive. Now, the examples that we have, I think, are intuitive, but we're using those to kind of get our feet wet on how to do this, what we say analytically. We're proving these analytically. All right, so here's our first one. We want to show that the sequence 1 over n converges to 0. So just to get an idea what this looks like, and I do advise doing a lot of scratch work on these things. So I'm just trying to think about like what 1 over n is. Well, that's the sequence. Well, n is a natural number, so if I start with 1, I get 1, and then 2, I get 1/2, and 1/3, and so on and so on. And I think intuitively we can see that as my denominator grows, this thing is going to trend towards 0. Right, so we think that this sequence converges to 0 is the way we say that. But we have to prove it analytically. Now, in the scratch work, I think it's actually more helpful to start at the endpoint. Okay, so what we want is something like this. According to my definition, I need 1 over n minus what I think the limit point is, which is 0. I need that to be less than epsilon. Okay, so somehow I've got to pick a capital N, such that when every little n past that, or when we have a little n past the capital N, we get this inequality here? Well, I mean, let's just do some work. Look, 1 minus n minus 0 is still just 1 over n. Okay, so that's true. And since n is positive, 1 over n is always going to be positive. So we have this situation. 1 over n is less than epsilon. And actually, I could multiply both sides of this inequality by n and divide both sides by epsilon to end up with 1 over epsilon being less than n. And that's going to be true because n and epsilon are both positive, so my inequality doesn't flip or anything like that. So I have this 1 over epsilon is less than n. Aha. Why don't we let capital N be the 1 over epsilon? Because if it is, let's follow the logic. If I have a capital N at 1 over epsilon, and I pick a n greater than that, then that's going to be true. This inequality is going to be true, which means that 1 over n is less than epsilon, which means the absolute value of 1 over n is less than epsilon, which means that the absolute value of 1 over n minus 0 is less than epsilon, which is exactly what we wanted to show. Okay, so I think we can string all this together to get a really good proof. Let's try it here. So proof. You always want to start these out with, let's let epsilon be greater than 0. Okay, and then we decided to let n be 1 over epsilon. So let's also let capital N be 1 over epsilon. So then if n is greater than capital N, we're just going to use my scratch work to work backwards. And so we can say this. We can say the absolute value of 1 over n minus 0, which is we know to be 1 over n, is going to be less than 1 over capital N, which is less than 1 over epsilon, which is just, since I'm dividing by a fraction, just epsilon. And that's all I really wanted to show, is that according to my definition, if a sub n minus my limit point is less than epsilon for any epsilon, once I've passed this capital N value, then I've shown convergence. So actually we just did it. So we say we can write it a lot of ways, but the one I'm going to choose to write it this time is that the limit of the sequence 1 over n equals 0. End of proof. I hope that makes sense. We're going to try a couple more just to get used to this idea. Okay, so now this time we have a new sequence, 2n plus 6 over n minus 1. And I'm thinking back to like Cal 1. I know that if n goes infinity, this thing would go to 2 over 1, which is just 2. So I think I have a pretty good idea of my limit point. But notice that is actually an intuitive way to do this. But we're trying to be more analytical, right? Okay, so let's get into our scratch work again. And let's see if we can figure this out. So what we want is the absolute value of 2n plus 6 over n minus 1 minus 2 to be less than epsilon. Okay, now from here I'm just going to do some algebra to kind of simplify this a little bit. I can get common denominators with the n minus 1 and the 2. So I end up with 2n minus 2 in the numerator. And I didn't affect the inequality at all, I just got common denominator. Okay, so if I bring that together, what happens? The two n's subtract out, and I have 6 minus negative 2, so I have 8 over n minus 1 is less than epsilon. Now, 8 is going to be positive, n minus 1 will be positive, so I have 8 over n minus 1 is less than epsilon. Solve for n here, and if I do, I think I can find what my capital N needs to be to prove our limit. So we're going to do a little bit more arithmetic here. I know that then the 8 is less than epsilon over n minus 1. And so n minus 1 is greater than 8 over epsilon. And so 8 over epsilon plus 1 is less than my n value. And that's what we want to let be capital N. Because if I have an n value greater than capital N, then I'll cycle back through my logic. I end up with exactly what I wanted, being less than epsilon. Alright, so now that we have that, I think we're ready to write our proof. And basically, if you notice, what I'm doing here is just I'm solving for little n. That's how I pick out what my capital N value should be. Okay, so we have proof. We're going to let epsilon be greater than 0 and let capital N be this 8 over epsilon plus 1. Okay, so once I have capital N is 8 over epsilon plus 1, I can use all this previous algebra that I've had to help me get basically this statement here that 2n plus 6 over n minus 1 minus 2 in absolute value is less than epsilon. Alright, so I'm just going to work my way backwards. So then if n is greater than n, little n is greater than capital N, then we have that 8 over epsilon plus 1 is less than n, which implies, just doing our mathematics, and we can check through our scratch work as detailed as needed, that 8 over n minus 1 is less than epsilon. Thus, I can say 2n plus 6 over n minus 1 minus 2 in absolute value, which equals, according to our algebra, the absolute value of 8 over n minus 1 in absolute value, which is the same as 8 over n minus 1, is less than epsilon. So here, again, what this means, and it takes a little while to see it, but if I get past this point, so remember my graph, once I get past this capital N value, all my sequent terms are going to have to be really close to my limit value, which in this case is 2. So we showed that, look, as long as I get past this point, once I get past that point, and that point here is 8 over epsilon plus 1, then all of my sequent terms are going to be very, very close to the value 2. They're going to be within epsilon away from the value of 2. Alright, so we can say thus, and this time I'll say 2n plus 6 over n minus 1 converges to 2. End of proof. I hope this makes sense. Let's try one more. Okay, this time we have 7 minus 1 over the square root of n. And if I think just intuitively, I believe the limit of that is going to be 7, because 1 over root n is going to trend to 0. But we need to prove it. So again, we're going to do our scratch work to help us figure out what our capital N value needs to be. What is it we want? We want 7 minus 1 over square root of n minus 7 to be less than epsilon. So if you notice, that means then that 1 over square root of n negative within absolute value is less than epsilon. Okay, so which means I can drop the square root of the absolute value, right? So then just divide by epsilon, multiply by root n. I get 1 over epsilon is less than root n. So then n is greater than 1 over epsilon squared, and that's the value of capital N that I want to use. If capital N is 1 over epsilon squared, then I can trace backwards through my algebra and eventually get exactly what I wanted. Alright, so let's try writing this up as a proof. And I'm first going to start off with saying let epsilon be greater than 0 and capital N be 1 over epsilon squared. Okay, so if then n is greater than 1 over epsilon squared, I'm going to just trace through my algebra here a little bit. That means then the square root of n is greater than 1 over epsilon, which means that 1 over root n is less than epsilon. Okay, so what I wanted, which is the absolute value of 7 minus 1 over square root of n minus 7, equals the absolute value of negative 1 over square root of n, which equals 1 over root n, and that's greater than epsilon if little n is greater than capital N. Alright, so once little n gets bigger than capital N, you can think of capital N as kind of your boundary marker running in the x direction. Once I get past that marker, all my values are within epsilon away from my limit point. That's exactly what we're trying to say here. Okay, so thus, we'll just say the limit of a sub n equals 7. End of proof. I've shown you 3 different examples. They're all kind of the same flavor. Again, the scratch work is very helpful because it helps you pick out what epsilon is. Okay guys, I hope this makes sense. I'll try to do some more examples for this if it's helpful. Just keep working at it. You got to understand this definition. So go back over the figure that I showed and let me know how I can help. And have a great day. Take care.